this is nothing but Ex given H. Ex given D and H is nothing but Ex given H. Because X is another data point. Right? Okay. So instead of taking the sum, I want to take the element in this sum that is the maximum. Okay? So basically I can then consider the hypothesis Hi that makes Px given Hi times Phi the highest. You see what I'm saying? No, actually no. So Pt given Hi times Phi the highest. And to do this, essentially, I can basically, then you do log. So P log of Pt given Hi plus log of Phi. Okay? If you maximize this, this is called MAP. Maximum a posteriori hypothesis. That hypothesis that has the highest posterior probability. That's still not maximum likelihood. Then next you'll say, since I'm sunk anyway, I'll say forget about this guy. I'll just go with log of P given Hi. And look for Hi that maximizes log of the probability of the data given the hypothesis, which also maximizes the likelihood of data given the hypothesis. That's where maximizing likelihood comes. You see what I'm saying? After 2 steps of huge simplifications, you fall into the usual thing that you all know and love, which is maximizing likelihood. Now the interesting questions then is, of course this itself is a huge problem. You should never have done this. And then going from here to here is another huge problem. If you're thinking in terms of why is it reasonable to go from here to here, you can ask the point that you can see that Pd given Hi is nothing but P d1 etc. dn given Hi. Because the data points, the n data points. Which, because H causes all the datas, is P d1 given Hi times P d2 given Hi times etc. P n given Hi. Plus still P of Hi. Now when you do the log of these, they will be log of this, plus log of this, plus log of this, and so on. Which sort of tells you that as the amount of data increases, in this sum here, this factor dominates. So for the fully large data case, maximizing likelihood is as good as maximizing a posteriori probability, which then maybe is as good as Bayes. But for the small amounts of data, that's not. Okay? So that's basically Bayes networks. So the other thing that, there's still 15 more minutes, and I want to mention something very useful. You should look it up in the slides, that Bayesians and frequentists don't get along. And remember, Bayesians basically say hypothesis as a random variable. Frequentists say that, first of all, Bayesians say probabilities are made up. You can decide what your probability is. Bayesians are essentially individualistic. Okay? All Bayesians say, remember that's what I asked you. In the Bayes network, can you put CPTs in such a way that the network will blow up? No. It will never blow up. You can put any numbers you want. The only thing that Bayesians ask is, if you believe in certain probabilities, make sure that you live your life with those probabilities. Be consistent with your probabilities. Frequentists say probabilities are objective. They don't depend on wishy-washy thinking, like I feel like there is about 0.7 probability that I will get an ice cream as a result. I can't say that. So in fact, the classic example is, what's the probability that at 4 o'clock on March 1907, Einstein had a large cup of tea? How many of you are ready to give some number? The guys who are ready to give some number, you are Bayesians. The frequentists say, this question doesn't make sense. You cannot set up an experiment unless you believe in Groundhog Day, right? Is that the Groundhog Day? That's the name of the movie. Einstein has to keep going through that particular day at that particular 5 o'clock about 1,000 times, and you see how many of those times he had a big T, and then you say, okay, this is a probability. So that's why frequentists don't get much business, because any probability you ask them, they'll say, well, it can't be answered. Bayesians, on the other hand, you want a number, we'll give you a number. So they're full of people. But then, and then the Bayesians think the hypothesis is a random variable. Frequentists think hypothesis is not a random variable. But they both agree on one specific technical method, which is maximizing likelihood, MLE, maximum likelihood estimation. There, the Bayesians say, you look at MLE, Bayesians say, hey, MLE is nothing but Bayes learning after 2 approximations. First map, then MLE, then you have MLE. And the frequentists say, yeah, we can live with this too, but just don't go around calling it as P D given H, maximizing P D given H, call it P D colon H. Then we'll be in business. Because they don't believe H is a random variable. And if it's not a random variable, you can't put it on the side. That's also a huge religious war that used to rage in the statistics departments. And the frequentist won for a while, then Bayesians took over. Then, as I said, both of them are in a corner, while the layer people are having. Okay, I'll stop for the regular session and we'll see if there is a way of getting these things set up.
Well, there's one way up.
Okay. So maybe if you guys have the slides, you can actually look at the slides as I'm going to do a core imitation of them on the board. Okay. easy enough actually, it's mostly right. Okay, but before I remove this, is there any question? Are there any questions on what we have done? Okay, so this is a long preamble. Essentially, when you think you learned Bayes network learning, the stuff that you learned is the one that I'm going to do in the next few minutes. But I don't want to do that because that's like just doing something without knowing why you are doing it. This basically tells you why you did what you do. Yes?
You said neural networks are second-order approximations of Bayesian learning?
No, neural networks are just yet another maximum likelihood estimates. So they are second-order approximations. Okay? Doing math approximation is, first order. I mean, there is no real first order versus second order, but I mean, I went from the sum to the element that gives the maximum value to the sum. And then that sum involves both the d given h and thus the prior probability of h itself. And by the way, so one of the interesting things is actually, this is a very useful thing to understand before I go forward. Remember I said regularization is understandable from the Bayesian learning point of view? This is regularization. If you are basically starting from this side, you didn't know how you fell from heaven, and you're on earth, right? You fell from heaven to the middle ground to earth. And things are going bad, and you're trying to reimagine what could have been better. Okay? The full is of course doing Bayesian learning, but the other is at least trying to see which hypotheses are more versus less likely. In doing the optimization, I want to not just pick a hypothesis that maximizes the likelihood, but also pick a hypothesis that maximizes the likelihood while making some assumptions about what hypotheses are more likely, what are less likely. Right? And so if you remember the double U descent, and I said they do regularization. So the regularization they do, they assume that none of the weights in a reasonable neural network would be too big. Because allowing any single weight to be infinitely large makes the network essentially learn grandmother neurons. That means it memorizes the data. Right? So you essentially, by putting a regularization constraint, you are equivalently making a decision about prior, which you remove willy-nilly. Again, if you came this way, you know what you threw away, and so you can try to reconstruct it. If you came this way, you have no idea. Everything looks like, I'm lost, I don't know. And most machine learning courses go this way. Which is why you have this nonsense about learning is optimization. Oh, actually not optimization, optimization plus some extra stuff. Oh, it's not even that, plus keeping lots and lots of hypotheses. Well, it's because you're supposed to do the first one. Okay? Any questions? Okay, let's go forward. And then I just basically want to get you started in the maximum likelihood estimation for Bayes networks, and then I will give you the video with the slides that you can watch later if you want. Other people anyway have to watch. This would be interesting because it's been like a million years since I did work Bayes. Okay, so think about the following simple scenario. Okay, so I'm basically considering again something like this candy scenario, where I have a bag from a new manufacturer has theta% of cherry candies. Okay, so there's a bag of candies, and this might contain theta% of cherry candies. Okay, so then the Bayes network that I have in mind is probability, it's just basically theta. Okay, and theta is probability that the flavor, it's not here. So when I pick up the candy, then I get the flavor, and the flavor is either cherry or lime. Okay, so essentially I have flavor is the random variable. When I pick a candy, its flavor would be the cherry or lime. And theta basically says what's the probability that a flavor is equal to cherry. That's it. And that's basically flavor, right? If you know probability of cherry, then you know 1 minus that is the probability of flavor. This is a Bayes network. Doesn't look big, but it's a Bayes network. Right? So, except now, notice previously I did the same thing, except I considered theta equal to 0.25 and theta equal to 0.5. Only two thetas for my example. Now I am allowing theta to be a continuous variable. So, any probability. Now if I get a whole number of candies, essentially then I just want to maximize the likelihood. I am going to go with that last method. Maximize the likelihood. So, for example, if I have seen n candies, okay, of which L are lime candies till now and C are cherry candies till now, okay, then the probability of seeing these candies, L lime and C cherry candies, is to see cherry candies theta power C. Right? For each cherry candy it's theta. C of them, theta times theta, theta power C. The other one is lime, it's 1 minus theta power L. This is the likelihood estimation. This is the likelihood expression. This is the likelihood expression. Okay? I just need to maximize this expression with respect to theta. This is a continuous expression in terms of theta. I just need to maximize it with respect to theta. So, to make my life simple, I will decide to take the log of this and maximize that instead. It's okay, right? Because if the function, if I'm trying to find out the fraction value of the function, if I take the log of the function and find the place where the maximum occurs, that's the same place. The other function also has the real function also has the maximum. The actual value would be obviously e power, right? So I want to do the log. So there will be log of theta power C and 1 minus theta power L, which is C log theta plus L log 1 minus theta. Right? It's like a high school calculus. Right? At this point, I need to maximize this with respect to theta. Right? Now, it turns out in this particular case, essentially there is only one function, one variable theta. It's not multi-variable maximization. So I just essentially, no, actually, sorry. Okay. So I need to maximize the value. I need to find the value of this function, the theta value where the likelihood becomes like this. It's a single variable optimization. Okay. So then I take derivative of this d by d theta of C log theta plus L log 1 minus theta and equate it to 0. Remember, normal gradient descent would be used when actually to do this, finding the place where the gradient became equal to 0. But it turns out for this particular case, you can analytically solve it. Okay? You can analytically solve it, and if you do this, essentially it will be C by theta plus L by 1 minus theta. And then there is a minus. because of the minus theta. Equal to 0. And you compute theta. And you'll get theta equal to C by C plus L. C by L. You say, did I waste my time hanging around the class after regular period to find out something that I would have done without you wasting my time? You do this all the time. But you do a whole bunch of things in your life all the time without knowing why the heck they want. This is the reason you are right in assuming that of 100 candies, 20 are cherry candies. Assuming that the probability of cherries is 20 by 100 or 20% is coming directly from maximizing the likelihood. Okay? This is the first definition, first case of Bayes network. The next thing that I want to show you is, this looks as if this is too easy, right? The next thing I want to show you is consider, so this, I want to take this out. Again, all of these are slides that are available. Consider a more interesting case. Let me draw the case while I remove the stuff. Now, I have a flavor which then causes a wrapper. So previously, all candy boxes came in the same plain brown envelope. Okay. Now basically the envelope, the wrappers would be either green or red. It's to sort of indicate whether the stuff has lime candy or cherry candies. You see what I'm saying? Okay. So then the question is, this is my Bayes network now. Right? Flavor basically leading to the wrapper. Okay. So red green wrapper depends probabilistically on flavor. It's not deterministic. It's not necessary that all cherry bags will only have red wrapper. Okay. It's deterministic. It's kind of probabilistic data. So the question then is that, so then I have, how do I specify this probability network? So I have, first of all, notice that here I gave, in this case, just like previous case, I gave the topology of the Bayes network. It's a small Bayes network, but I gave you the topology. Okay, so what kind of probabilities do I need? I need one probability parameter called probability of flavor equal to cherry, which we'll just call it theta. Okay? And I need a conditional probability table here. Okay? Which basically says, if the flavor is cherry, what is the probability that the wrapper equal to red given flavor? You see what I'm saying? That's the probabilistic dependence. If the flavor is cherry, let's assume that with theta 1 probability, the wrapper would be red. And if the flavor is lime, with the theta 2 probability, it would be red. Now, by the way, is theta 1 plus theta 2 equal to 1? No. I still need to figure out all these numbers. All we know is, if it is cherry with theta 1 probability, I will actually put the red. Okay? But 1 minus theta 1 probability, I will still put a green. And say, ha ha, you thought it's cherry, but it's actually lime. You see what I'm saying? So that's basically the deal. Okay? So now, this is your multivariable calculus minimization problem. Because you have theta 1, theta 2. Okay? Now the interesting thing is that, take a look at that and so imagine that I have seen n candies, okay, then of which R are, and N candies, which are, C are cherries, L are limes. Okay? RC are cherry candies in red wrapper. LC are cherry candies in green wrapper, GC. Cherry candies in green wrapper, and so on. Okay, and similarly here are L and GL. Okay, these are numbers that I can just see as I keep getting packages and open it. I know how many I got actually. Let's say 100 of which C are cherries, L are limes. Of the C cherries, RC of them are actually having red wrapper. GC of them are having green wrapper. Now, of course, clearly GC is C minus RC, right? And similarly, GL is L minus R. These are the numbers. This is the amount of data I got. Now the question then is, I need to write, in doing Bayes network parameter computation, in general statistical learning, all you really need to do is set up the likelihood equation, likelihood expression. That's it. Okay? I need to set up the likelihood expression. And then of course then I do the calculus. So let's get the likelihood expression. Earlier it was easier. Remember, it was n of which C was cherries, and so then theta power C and 1 minus theta power L, that was it. Now basically it's split into 4 different cases. Okay? So I will write the expression and then try to make you understand that. So if there are C cherries, then theta power C. So consider a specific data point. Okay? A data point which is a cherry in green bag. I just saw a cherry in green bag. What is its probability? Cherry, so it's theta. In green bag, no, cherry, it's cherry. Okay? And then the green bag, because it's in, its red bag is theta 1, so 1 minus theta 1. Do people see this? For each cherry in green bag, I have to multiply that quantity. Now if I see a cherry in red bag, I will do theta times theta 1. Okay? So the overall expression, I'll write this and then I'll answer that question so you can see whether you can agree with me. 1 minus theta power L and theta times. So this is the part for seeing C cherries and L limes. And then of the C cherries, I found RC of them in red bags. I found the GC of them in the green bags. Of the limes, I found RL of them in the red bags and GL of them in the green bags. This would be the final expression. For each data point, I will get like the theta times theta 1, theta times 1 minus theta 1, 1 minus theta times theta 2, etc. If I multiply them all, then I will get this big expression. I need to find the minimum of this expression. Now this is a 3-dimensional function. Actually, it's a 3-argument function. It's like basically, right? Basically, it has 3 parameters. theta, theta 1, theta 2. What? I mean, so the three inputs and then y. That's what I mean. So the input dimensionality is 3. Okay? So it's you know, a y equal to, this is basically of the type f, y equal to f of theta 1 and theta, theta 1, theta 2. That's your function. And now I'm trying to find the maximum for y. Okay? Now what happens is, this is essentially going to be gradient, actual gradient. But you guys know, actually you came to this from gradient descent, and you say, let me just do the gradient descent. But it turns out that all these cases are actually cheap, easy. Here you can set the gradient expression, equate it to 0, and we'll be able to solve it. In particular, you need 3 partial derivatives, right? So if I call this likelihood, this is the likelihood of theta, theta 1, theta 2, is this likelihood expression, and this likelihood expression can be taken, I can take the partial derivative of dou L by dou theta, dou L by dou theta 1, dou L by dou 2. Compute each of them and equate them to 0. Now, before I do it, think of what could happen. I can get 3 equations, and I have to solve 3 equations. In the worst case, the 3 equations would be simultaneous, nonlinear equations. If they are nonlinear simultaneous equations, there is no analytic solution. Then you essentially need to, basically to solve it, you might as well use Newton-Raphson method, which is like basically doing gradient descent to begin with. Okay? But what is interesting is for Bayes networks, where you have continuous data, you have complete data. That means you always see the data with all its attributes. So for example, in this case, what does complete data mean? If I said, I have a data point, what are the questions you would ask me about the data? What's the flavor? What's the wrapper? If I can answer both, then I have the complete data. Sometimes, for example, I'm not allowed to open the bag. So I only know the wrapper. I don't know the flavor. You see what I'm saying? Then the flavor becomes hidden variable. If you have hidden variables, doing Bayes network learning with hidden variables leads to an idea called expectation maximization. Because with the hidden variables, you need to sum likelihood.